Hey there, Code Wranglers. Welcome back to Conquering the JavaScript Interview, where we're going to turn the enigmatic world of programming into your digital playgrounds. So today we're going to gear up to harness the subtle art of Bitwise Operations in my little continued series here on Bitwise Basics. We're going to start by shining a spotlight on a very nifty trick, how to set a specific bit within a number. It may sound like a small feat, but it's a mighty power in the realm of coding. It's going to lay the groundwork for some sophisticated features and functions. We're leaving that in. So, I would like to remind you all in the description down below, there's a link to Covalence's community membership where you're not just going to get over 300 hours of cutting edge coding content, you're going to get our entire full stack program, my comprehensive React course for just $25 a month. You're also joining a vibrant community where learning never goes into standby mode. Any new updates on our courses or any new courses I make in general, they're yours for free. Stay current, stay connected, and stay coding with Covalence. So, buckle up because we're about to embark on this next binary quest in this Bitwise Basics series. Now, today's problem is a little bit abstract in the sense that, unlike the very first XOR one that had a very obvious input and output, this one, again, is all about binary, and the problem is very straightforward. The code is straightforward when you understand how it works, and I'll try and break it down into comments as always. We're going to get coding as quick as possible. Find the CodePen prompt. Find the prompt in the CodePen, rather, in the description down below. The fully solved thing will be down there available as well. And you are welcome to grab it and paste it into your own code editor or just use a copy or fork of my CodePen. Remember, I do advise that you delete the solved code and write along with me, even if you don't know what's going on, or give it a shot yourself to see if you can figure it out. But today's problem is we have a function called setSpecificBit. That's it. Its entire job is to find one specific bit in a series of zeros and ones and find one to set it to the number value of 1. So our input for this one is going to be a number in which a bit needs to be set. So a whole integer that we convert into binary, and we're then going to look at a series of, surprise, zeros and ones. Then the second parameter to this function is a position integer that will specify which bit position in that number, right, starting from the least significant bit, do we toggle over to 1. And then from there, the output should be the modified integer with the specified bit set to 1. So just like our code, it says here, we take a number, convert it to binary, look through that set of numbers to the position we're looking for as our second parameter, and then bam, change that from a 0 to a 1. So set a bit. That's all we are doing. So some example usage. If we call that specify bit with the number 5 and the position 1, we expect a output of 7. Now that doesn't make sense if you're not familiar with Bitwise Operations. Again, I couldn't tell you that off the top of my head. I would have to actually write it out to figure it out, which we're going to do together. But the important thing is here is if you look at the binary representation of the number 5, it is 1, 0, 1. And if I say we set the bit at position 1, we then go to position 1 because our leading is our least, what did I call it? The LBS, right? I just said the word and I already forgot what it was. Least significant bit, my goodness. That's starting from 0. So thankfully it starts counting from 0 just like we're already used to in JavaScript, our array indices starting from 0. So our least significant bit and then position 1 will be right here and bam, we convert it on over and call it a day. And we set that from 0 to 1 and boom, we get that. And that is the number representation of 7. So that's what that output is. I'll go over these two as well when we get there because there are some nuances to them that are a little bit different than this more simple one over here to look at. But we're going to get there when we get there. Nevertheless, I'll copy and paste these down below as always for our output. So, like I said, our function, setSpecificBit, number, and position. So let's see if we can figure this out, and this is going to be done with our favorite friends, our new friends rather, in my little mini-series here, the Bitwise operators. So in terms of the operators we've worked with thus far, we have done and in the last video along with right shift, we have done the XOR operator, which was that up one, the exclusive OR operator. And I think that's it, because this video is going to introduce our friend the OR operator, and it's going to also introduce the left shift operator. And if I'm not mistaken, that means we're only left with one that we haven't worked with yet, which is the not operator. I might be missing something, but that seems right. So, those are our Bitwise operators. As a quick refresher, you can always take a pause and watch my previous 2 videos if you're stumbling upon this for the first time, or you can always just bring up the MDN docs of Bitwise operators just so you can get their information at a glance. And even if you know what that means, at least you have them at your fingertips to be looking at, or your eyes to be looking at on your second monitor, your third monitor. I need like a fourth and fifth monitor over here, but I'm not going to get ahead of myself. Okay, so like I said, this one's going to focus on our good friends OR and left. So there are 2 new ones we're going to be encountering in this video compared to previous videos. As always, I've made some quick diagrams that are also available as Imgur links down in the description below. You can click on them, open in new tabs, and take a gander at them. They're almost kind of like quick study cards, like flashcards to study the information on certain operators as we cover them for a specific solution. So first things first, let's see how simple we can code this particular solution here. And when I show it to you, it'll be one of those things where the code, again, is extraordinarily simple, so I'm going to try and get to it quick. Then we'll talk about the explanations after. So first things first, we need to know what position we are switching our bit in. And the easiest way to do that is to make a stencil, if you will, a mask of sorts, saying, hey, this represents where we want to set a specific bit to. So this, in actuality, is called a mask. You're going to think of it as a stencil. So we're going to call it mask, and it's very simple. We're going to take a simple number that can convert to binary easy, such as the number 1, which is just 1 in binary, and we're going to left shift this now, the number of positions that we want. How did that just happen? How did I manage to type all that in so incorrectly? There we go. We're going to left shift it a number of positions that our input tells us. So that generates a mask. Basically, it'll be a 1 with a bunch of zeros behind it, and the bunch of padding zeros that we add behind it, as in to the right of it, because we're shifting the 1 to the left, hence the term left shift, that 1 will be in the position that we want to set a specific bit to. That's the whole magic behind this. That's why I'm telling y'all, remember the mask as a stencil. I'll give you a more extensive analogy after the code. But that's a quick and dirty way to make a stencil or mask for our code, where the 1 is where the forced position switch is going to happen. And then all we have to do is return number or bitwise mask. So basically, we're going to take our input number, which will be converted to its binary format. It will then be ran with the bitwise OR logic, not logic, but bitwise OR operator that will then run its determination against the mask. It will then convert that binary number, and then the return will convert it back to an integer and report it to us, and it works just like that. So let's take a look to see if I am jerking your chain or not. We're going to go ahead and do a 5 and 1. Boom. I should probably console log something here, buddy. Let's go. And yeah, the expected output was indeed 7. So again, y'all are looking at that and you're like, cool, Luke. This doesn't tell me too much. And I know, I was there in your shoes not too long ago. But I will explain how this works, but we're going to take a little detour because, again, this is it. This is all the code you need to get this done. This has a fantastic time and space, big O complexity, and I will show you what this looks like, how to do a set specific bit in JavaScript if you don't know bitwise operators, and you will see how much faster, how much better, and how much less overhead this solution has if you understand it. Now, there's actually something interesting I'm leading up to with this Bitwise series, and that's going to be covering one of my favorite reads on Wikipedia, which is about the least in... Oh my goodness. One of my favorite ones forgets it. Fastest inverse square. What is it? The Doom algorithm. Just look up the Doom algorithm. Fast inverse square root. I knew what it was. Who said I didn't? All right? Get in the comments if I look like a fool because I didn't remember the name of my favorite Wikipedia entry to read. But yeah, if you ever have encountered the term fast inverse square root or the Quake 3, not Doom, Quake 3 algorithm, you have actually seen bitwise operators in their magic. So you'll actually be able to understand it a bit better with what I'm showing you here. Get it? A bit better? Anyway, okay, back to what I was trying to do here. Let's take a look at my diagrams. You can open the Imgur links in the description down below of what's happening here. Let's remind ourselves, left shift. If you're here in this video, then that's fine, we'll pick it up. But if you remember from the last video, we talked about right shift. It's the exact same thing in the other direction. So Left shift's specific definition, it's the two less than signs pointing this way, pushes all the bits in a binary number to the left by a certain number of places, specified by the 0 operand, or the second operand, filling in from the right with zeros. So that is how our mask fills in a bunch of zeros on the right-hand side of the 1. It shifts the 1 over and fills in the rest with zeros, right? So you're going to think of a conveyor belt with bit and byte, our two buddies that we've been using in this example, with a series of boxes to their left, and every time the left shift button is pressed, they both hop into the box next to the left. If somebody's on the edge, they hop out into oblivion, and then every single time that left shift happens, a new box appears where a 0 enters from the right-hand side. So in terms of specific numbers, if this is our before, 10110, and we do a left shift position 1, what's going to happen is this 1 jumps off into oblivion, then the 0 becomes our new leading or trailing number, our greatest significant bit. Then we get 110, and then a new 0 pops at the end right there, and that's what we generate. Now, after 2-bit shift, remember, these 2-bit shifts are going from the before. So if this is going back to our before number, if we do 2 positions, then the 1 and the 0 jump into the void. They jump into the shadow realm and explode. Then the 1 and 1 over here become our leading numbers, and then we fill in 2 zeros at the end to get 11000. So 110 and then 00 at the end is how we wind up with those two numbers, with this 1 and 0 jumping off into the oblivion. And with a simple example right here, it's just the same one from the other video, the previous video in this playlist, just pointing to the left instead of to the right, because this is a left shift. So like I said, the leading 1 will jump off into the void, 0, 1, 1, and the new 1 from the right-hand side. That right padding now pops in on left shift. And there you go. That is the entirety of what left shift is. It's pretty straightforward. It just shifts all the numbers on over. Then, the OR operator, we haven't covered this one yet. So the bitwise OR will take 2 binary digits, and it gives back a 1 if either or both of the digits are a 1. The only time you get a 0 is if both the digits themselves are a 0. So we're going to imagine our bitwise OR as a club bouncer. He's a bit more relaxed than the AND operator, because remember the AND operator was the mean club bouncer. This is the nice, relaxed club bouncer. He's going to let people through as long as at least one person in a pair has a VIP pass. So our two friends, Bit and Byte, approach the door, and as long as Bit or Byte have a VIP pass, or both, doesn't matter, both, one or the other, they are allowed in, which is our result of 1. They got in the club, y'all. Let's go. But if they both don't have a pass, well, this kind of makes sense. They can't get in. That's a 0. So in terms of our numeric examples, 0 or 0 gets us a 0. There's no choice there. 0 or 1, hey, one of them's got it. We get a 1 output. Again, reverse is also true. We learned about this being called commutative, where the order is not important. So if it's 1 or 0 or 0 or 1, they get, hey, y'all in. Come on in, y'all. They can come on in. And if they're both 1s, then that's no surprise. It's also going to result in a 1. I mean, that's really not too surprising. And then the diagram you typically see in like computer science or circuitry or things like that looks like this. Remember, the AND one had the flat butt, and the OR has the concave butt right there. And then the exclusive OR had the additional line on the inside lining it, if you're trying to remember what they look like. So, yeah, this is our friend the OR gate and the logic for it. Having this little table can be handy when you're trying to determine it, but it's fairly straightforward if you remember the analogy. The relaxed club bouncer. As long as one of y'all got a pass, both of y'all can get in. I don't care that much. So that's going to be how you're going to imagine our logic happening here in just a moment. So this is what happens. We make a mask, which is the number 1, or the bit 1 being pushed into the position we want to toggle it in our number. We convert the number to its binary format. We run the logical OR gate on each like column of bits that line up and against the mask. And then that final number will have the specific bit go from a 0 to a 1, which will output the correct number. So let's try and break this down. Then I'll give you all a more technical definition of mask, the identity, properties of left shift and OR and all that kind of fun stuff. And Big O, we'll talk about that. But let's look at the first example here, and then we'll come back and look at the others. So first thing is first. let's make our mask based on the 1 left shift position. So 1 left shift position also of 1. The binary representation of 1 is 1. And if it shifts over 1 position, we then get a 1 or a 0 right there, I'm fairly certain. I mean, that sounds right. Yeah, because it has to be. So, we've shifted it over 1, and that number right there, I can't tell. I mean, 1, so, if that's 0, 1, 2, because that's 3, right? Yeah, that makes sense. So that's 2. That is the nut. I know what this is. Am I really having to do this? Yeah, 10 is 2. Oh my goodness. I was like, I second guessed myself so hard right there. So this is our mask. We got a 1 and we shift it left by 1 space, aka there's nothing. So in this case, there's no 0s and 1s and other things around it to drop into the void. And again, all we do is move that 1 because there's nothing in front of it. We just move it over 1 place and add a padding 0 in front of it. This is our mask. This is a mask that in the second position has a 1 in it. And what we know about the OR gate, the OR bitwise operator, is that as long as there's a 1 present, it will result in a 1. This is the trick to it. So this is our stencil. This tells us at position 2, we have to toggle a number. Now, if the mask is not big enough, we just add padding 0s on the left-hand side, because as long as none of these values to the left-hand side are 1 that I'm adding here, this is still 2. It has not changed in value. It is still the representation of the number 2. So the mask will automatically grow in size with the left-hand side padding as much as it needs to, but always position 1 will be our toggle for the OR logic. So we can add as many 0s at the beginning as we want to, which is how we're going to solve this. So there's our mask. That's how we generated it. Our number 5, to toggle it to binary. So that's 0, 1, 2, 3, 4, 5. So we get 101 as our 5 right there as our number. So there's our number. We have our mask. Let's run an OR on it. So we have number or mask, and we'll say binary. There we go. So number or mask is our logic. So our number was 101. Our mask was 10. Right, and like I said, we can just add as many 0s at the beginning as needed in order to match the number of bits. Because again, every padding 0 on the left-hand side doesn't change the actual number it represents. But it does allow us to line up what needs to happen here and get our solution. So check it out. We add that extra 0 at the beginning there, and now we run the logic. If there's a 1 present, it becomes a 1. If there's a 1 present, it becomes a 1, and that's the one we've toggled. So that middle column is the position we wanted to toggle a specific bit on, which we did. The same OR logic applies to 1, 0. We get 1, hence the value 1, 1, 1, which we now know is 7, and that's, like I said, the expected output here. So voila, we have it solved. So that is how this one is broken down, y'all. That's what we're looking at here. Pretty cool, right? So like I said, that mask equals 1 left shift position. Creates a mask with a 1 at the specified position and 0s everywhere else, right? It moves all the bits to the left by the number of places specified by position. That's it. That's all it does. Then we apply the mask in number or mask. And that's number bitwise OR. You have to specify. Otherwise, if you say OR to a normal programmer that doesn't know bitwise, then they'd probably assume a logical OR, which is 2 straight pipes. Not without the password. Now, we're doing just 1 straight pipe, which is the bitwise OR operator. It compares every bit of its 2 operands, number and mask, and if at least one of those digits is a 1, it sets it to 1. So we ensure that if there's a 0 in our number, that our mask, our stencil, is what makes sure that that specific position bit sets to 1, and that's how it functionally works. I'll show you all what it looks like without Bitwise here in a moment, but I wanted to get in the technicals of what is a mask, because you'll see these a lot in Bitwise Operations, so it would behoove me to define it for you. Besides, hey, it's a stencil. That's our analogy. In the context of Bitwise Operations, a mask is a binary number used to select, modify, or view specific bits within another binary number. It's like a template that determines which bits in the target number will be affected or observed during an operation, right? So, how they are used. Selective modification. They allow you to change specific bits in a number while leaving the others untouched. For instance, setting, clearing, or toggling particular bits. Information extraction. Mask can isolate bits in a specific position or range, allowing you to extract and work with particular portions of a number. And then pattern application. Mask can apply a pattern of bits over a number, enforcing a structure or rule represented by the mask. Okay? So like I said, think of it like a stencil used in painting. Like a stencil covers parts of the canvas and leaves other parts exposed for you to stencil in. A mask covers or ignores certain bits and exposes others. That way, when you apply your paint, which is our bitwise operation through the stencil, the mask, only the exposed parts are affected. The rest of the canvas, aka all the other bits, remain unchanged. So that's what you need to think of it as. So if you get asked what a mask is in your interview and how do you use it, you're going to be like, it's like a stencil, right? It covers part of our canvas, exposes other parts. That allows us to do selecting, modifying, extracting info, or applying patterns of our choice on bits of a number. So, as a refresher, I'm going to do these in all these videos to really hammer this home. Bitwise operations operate on binary integers at the level of their individual bits. We've got and, or, not, XOR, left, right shifts. Okay? Left shift and right shift. Each one takes a binary data and morphs it in a unique way, following the rules of binary arithmetic. As our analogy from the previous two videos, string of Christmas lights, each bulb is a bit. Bitwise operators are like switches and how you can turn them on or off. Combine switches with and, light up more with a single switch with or, flip all the lights with not, or make sure only unique lights are on with XOR. The shift operators are like moving the strand left or right? That's all it does, and create patterns. You want to manipulate lights on a string of Christmas tree lights? These bitwise operators are where it's at. So things about or, you'll notice it's very similar to the and in the sense that it's idempotent, meaning bitwise ORing a number with itself doesn't change its value. It has identity. Bitwising OR with the number returns the original number. It doesn't annihilate like the other one. It returns the original number. It's commutative. The order of operands, whether it's A or B or A, doesn't matter, right? Doesn't matter what's on either side of the or, it's the same result either way. Like we saw in the diagram, it didn't matter if it was 0 or 1, 1 or 0. Both resulted in the exact same thing as we see here. It's also associative. I could put random parentheses over my entire or operation. It doesn't matter. The order of operation won't change the value whatsoever. So that's a lot of the properties you need to know about or. Now, left shift, just like the other one we looked at in yesterday's or the previous, because it might not have been yesterday's video, on right shift is a bit more complex in that it does zero fill, meaning as long as we keep shifting things to the left by X number of positions, it might potentially add X number of zeros right there. And it is non-commutative, meaning if I do start placing parentheses sets around shift operations of either kind, left or right, it will affect the answer because that is how many bits you may or might not be shifting at that time, etc., etc. So you won't get the same thing if you start placing parentheses sets around your shifting. And it is non-idempotent, meaning repeated application of left shift will yield different results every single time. It won't ever actually result back in itself, so it's not idempotent. So let's finish up our examples here and see if they all work. Let's see if we can do 8 and 2 together now. 8 and 2 expects an output of 12. So we do 8 and 2 gets an output of 12. We got 12 right there. So let's see if we can figure out how this one works. So first things first, our mask. Our mask is 1 shifted left 2. So 1 in binary is 1. Shift 2 positions on over. We got our mask. Our number is 8. Oh boy. So I should just memorize what these are at this point, so I know that's 2, 3, 4, 5, 6, 7, 8. Is that right? Oh, I miscounted. Oh, no. What did I miscount, y'all? Did I say 7, then miscount? Hold on. 1, 2, 3, 4, 5, 6, 7. Oh, yeah, I did miscount. 8. Oops. So there's our number in binary format. Here's our mask in binary format. And we know that if I need to match the number of bits total, I will add a padding left-hand side 0 to the mask so I can run the number or mask gate. So now we're going to do our OR. All right, our logical OR. There's a 1, there's a 1, zeros are zeros. And there you go. That number is 12. I'm going to trust that it's 12. Yeah, 1100. Or 1100, not 1100. Yeah, 1100 is indeed our 12 right there. That's what I like to see, y'all. That's what I'm talking about. So that's how it works. Now let's do it for our final one and see if we can't figure this one out together as I embarrassingly try and figure out what these numbers are and what they look like in binary, and I miscount and y'all make fun of me. That's fine. So let's generate our mask. 1, position 3. Our mask number will be a 1 shifted to the 3rd position, so we get that right there. That is our mask. Now our input number is 0. In binary, this one, oh thank God, this one's easy. In binary, our number 0 is 0. So all I'm going to do is place an appropriate number of other zeros to mask or to fit the length of the mask. So I basically add a bunch of padding here to make sure that my bits line up so I can toggle the correctly positioned bit as needed. I can add I can't, but I can theoretically add a gorillion zeros here to the binary 0, and it's not going to change its output. So our logical OR, 1 right there, and that is, yeah, that's 8, right? Yeah, we know that because we just did that. Hey, we knew one by heart for once. So yeah, we know the 1000 is the number 8. And that is our output of set specific bit 0 and 3. We did it, y'all! That's an 8, right? Okay, good. But yeah, hopefully it makes more sense of how you can make this mask, and you can see how it makes a stencil, saying, hey, just ignore all these and set this one for our OR operation to 1 at that position, which is exactly what it does. So it looks at our input, covers it with the stencil. That means that these 3 zeros get covered with the stencil. We fill in the 1 right there, and there's the stencil in action, y'all. That's what I'm talking about. And that is our result, which is indeed 8. If I can learn to type. There we go. Yay, we did it. So those are the 3 inputs that you're going to get for this one here. I did promise y'all that I'll show y'all how to do this with non-bitwise, but I'll have to specify first and foremost that the big O time for this one is a big O of 1, not 2, stop it, Luke, a big O of 1 with a space big O of 1 as well, meaning I think this is one of our most efficient algorithms ever, right? The bitwise operation of shifting and ORing is done in constant time. The number of operations does not depend on the size of the input. So no matter how big our number and positions are, the time does not change. There's no crazy iterating or no crap going on that we have to worry about. It's a big O of 1. That is literally just the flat line at the bottom that says, yo, dog, this is about as good as it's going to get. Now, in terms of space complexity, it's constant because it only uses a fixed number of variables, our mask, and the space to store the result, which doesn't really depend on the input size, right? So there you go. That is probably one of our best algorithms I've ever seen in terms of time and space. That is what I'm talking about, y'all. Now, in terms of why it's cool, direct hardware communication, any kind of low-level hardware programming, understanding how to set specific bits is pretty much essential when dealing with this stuff. Hardware registers, where each bit can control a different feature or behavior, is very common. Efficient data storage is what it's all about. Fine-grained control when it comes to writing algorithms, such as the Quake 3. I got it right. It's one of my favorites. Gets the name wrong, gets the game wrong, forgets everything. Sorry, being on camera adds this weird amount of pressure, even though most people seem to enjoy my style. And it's highly performant. That's why it's also so cool. Bitwise operations are incredibly fast because they're supported directly by that processor. In terms of real-world use cases, like I said, in hardware setting flag or configuration settings, specific bits toggle certain things at the hardware level. So knowing that Makes it really easy to do this kind of stuff with the bitwise operators we have learned here. Graphics, networking, game development, cryptography, all your usual suspects, as well as compressing algorithms are a big deal here as well. So this kind of stuff is used everywhere, y'all, and not just in these dumb little interview questions here. Even though, again, why it's cool is because you can flex on your interviewer and really show off that you know your stuff. So let's do the lmao function set specific bit non-bit. This is a horrible name. Oh my god. That is terrible. But you know what? Whatever. It gets the job done. Number, position, same thing. So how would I do this? I really should have planned this out beforehand. Let's convert it to a binary array. We'll do let in case I have to do something weird. Binary array. Take the number, convert it to binary string. Boom, we got it to binary string. Let's split it to an array so we have easy control over it. Now, because our binary positions are counting from the right-hand side, I do not want to do any kind of crazy length -1 math crap, so I'm going to be lazy and choose to simply reverse the array, so our least significant bit is now on the left-hand side of the array where our index position 0 is. So now the position will correspond correctly, and all I have to do is re-reverse the array before I return the number. So that's why I'm choosing to reverse it here out of sheer laziness. Then all I need to do is for however long the binary length of the array is, scroll down until I get to position, as less than or equal position, just keep on going. I need to add zeros. Remember, we're dealing with strings right now, not with numbers at the moment. I'm going to just push in zeros. This is our fake. We have to make sure that the array is long enough to accommodate our position. So basically, if the length isn't as long as our position, we're going to push in some zeros at the end of the array to basically pad it up. So basically, this is our fake left shift and our padding zeros being added should they need to be. That way, my binary array at the position we want, toggle it to 1. There you go. That's all it's going to do. That is why I chose to reverse it, so there's no crazy math here. All I have to do is say at that position, toggle it to 1. And then we have to convert it back to our result number, which is taking a parse integer of our binary array, reverse it back into the correct order with the least significant bit on the right-hand side, join it back into a single string from an array, and base 2 of parsing. We're parsing an integer from a base 2 value back into our parse integer. Then we simply need to return our result number. So you can see, it's not nearly as cool. It's not nearly as cool as our other solution here. Yeah, so 0, 3 results in the same thing, which is our result value of 8. So it works. It's just way less cool and a lot worse in terms of its big O as well. The big O time and space is still going to be time is n and space is n, right? Because the bigger the input number and position get, the longer this array that needs to be generated has to be, and we have to iterate over the thing potentially n number of times based on how big the length is and the position are of the array. The while loop will iterate at worst n number of cases, right? And we have 2 reverse operations on the entire array that contribute to that big O of n complexity. So it's all right. It's not it's a linear. It's not bad, right? In terms of algorithms. And then again, space wise, we got to create that binary array value, and it will be as big as n is, aka our number. So that's it. That's it for this video. Let me scroll back up to the cool solution. There we go. Yeah, that's what I'm talking about. Bitwise. Forget that nonsense down there. But yeah, as always, that's the secret to it. Hopefully it demystified some in front of your eyes. I'm having a ton of fun because this is something entirely new to me. I've known about them, like I've talked about. I've known about them, but I've never actually worked with them. So I feel like I've gotten and hopefully given y'all, hello Percy, some digital tweezers so you can place one light in a grand display of binary brilliance. So if today's binary ballet has limited your path in coding mastery, smash that like button, right? Don't forget to subscribe, hit the bell notification. We're just getting started here. I'd love to hear from you. Drop a comments, your revelations, or even the Bitwise wonders that you have encountered or crafted on your own. Otherwise, consider joining the Covalence community. Let's navigate these binary waters together. Stay curious, stay coded, and as always, keep on crafting your story.